close your eyes and drift upward, not just into the night sky, but back to the biggest stage imaginable, the universe itself. Except, not just one universe. You've probably heard people throw around the word multiverse like it's just a Marvel plotline, but the real scientific version is far stranger, and honestly, a little unsettling. You look up and see stars scattered across endless darkness. It feels vast, almost infinite. Or maybe it actually is. Physics whispers that beyond this sky are countless other universes, each one just as real as yours. And if every possible universe exists, then there are infinite versions of you right now, hearing these words. Which leaves us with a paradox. What does probability even mean if the unlikely still happens forever? Before we drift further into this unraveling of perception, allow me a soft pause here. If these reflections speak to you, consider subscribing so that more journeys like this can find you again. A quiet like helps this world of ideas reach further. And now there is also the hype button, resting beside subscribe and share. A single press can send these thoughts further out, rippling toward other curious minds. Last time, one hype alone gave my video an unexpected reach, carrying it further than I imagined. It truly matters. And if you wish, share a comment below. I would love to know from where in the world you are listening tonight. Sometimes a single message from someone halfway across the planet reminds me that this conversation is not a monologue, but a bridge stretching through space and time. The paradox begins with cosmic inflation. In the first sliver of a second after the Big Bang, space didn't just expand, it ballooned faster than light itself. Some regions slowed, cooling into galaxies and stars, while others kept stretching. The result is a never-ending patchwork, bubble-like universes budding off forever. Ours is just one. Another could be almost identical, except you chose pizza instead of pasta for dinner. Another might have completely different physics, where light behaves nothing like it does here, where matter might never clump into stars, and where time itself could flow in ways we can't even imagine. Here's the mainstream fact. The cosmic microwave background, the faint afterglow of the Big Bang, fits inflation theory beautifully. It's one reason scientists take the multiverse seriously. But here's the quirky twist. Some researchers suggest strange cold spots in that glow might be scars left behind by collisions between our universe and another. It's not proven, but it keeps the idea from drifting too far into pure science fiction. And whether or not those scars are real, the fact that they are even discussed in serious physics circles shows just how far this concept has moved from comic books into the frontier of cosmology. Now, imagine flipping a coin. In one universe, it lands heads. In another, tails. If there are infinite universes, both results occur infinitely many times. So what does 50-50 odds even mean? Probability, which depends on counting possibilities, starts to collapse under infinity. Physicists try to fix this with measures, ways of weighing outcomes across infinite sets, but those methods often give contradictory answers. It's like trying to calculate the average depth of an unending ocean, when every direction just keeps going without limit. Scientists still argue whether this makes the multiverse true science. Some say it's philosophy in disguise, since other universes can't be observed directly. Others counter that if the math predicts them naturally, dismissing them would be like refusing to believe in atoms before microscopes. Either way, the paradox holds. Infinity makes prediction unstable. Every event is inevitable somewhere, yet meaningless in the whole. For you, it raises an unsettling question. If infinite copies of you exist, what makes this particular life special? Some argue duplicates don't matter, you only experience one thread. Others worry it undercuts individuality. After all, if every choice is mirrored infinitely, then uniqueness itself becomes an illusion. It's the kind of puzzle that feels more personal the longer you let it echo in your thoughts. And yet, in day-to-day life, the paradox doesn't stop you from rolling dice, checking the weather, or betting on a game. Probability still works locally, where infinity can't overwhelm it. But once you zoom out far enough, the very concept of chance begins to blur. That's the multiverse paradox in its sharpest form. The moment infinity becomes real, the rules we rely on to make sense of the world stop behaving the way we expect. And perhaps the real wonder is not in solving the paradox, but in learning to live with it, knowing that even in a sea of endless possibilities, this single moment, this single version of you, is still here, still listening, still real. Imagine you're sitting at a desk, watching your computer run a simulation. On the screen, a little digital world unfolds. Characters walking around, weather shifting. Rules of physics ticking along in streams of code. Now flip the perspective. What if you're the one inside the program, unaware of the machinery humming behind the scenes? That's the core of the simulation reset paradox. If our universe is simulated, what happens if we build a simulation inside it? And if that one makes another? At some point, the chain risks looping forever, and no one can tell where the real layer begins, or if there even is such a layer at all. This thought experiment became famous after philosopher Nick Bostrom framed it as a statistical argument. If advanced civilizations can run hyper-detailed simulations, then simulated beings would vastly outnumber biological ones. By sheer probability, you're more likely simulated than not. And this isn't some late-night dorm room stoner musing. It's a serious argument that's been debated in academic journals, physics conferences, even in the quiet boardrooms of tech companies where engineers wonder what kind of machine could eventually hold worlds within worlds. Here's where the paradox sharpens. Today's supercomputers already simulate immense systems, climate models with billions of variables, galaxies clustering under gravity, even partial brain networks firing in test tubes of code. We're nowhere near recreating the full spark of human consciousness, but the trajectory is clear. More power, finer resolution, better models, deeper illusions. Now picture a future where a simulated being, convinced of its own awareness, boots up its own simulation. That nested world would feel just as real to its inhabitants. Stack that process again and again, and soon you're tumbling down an infinite spiral of realities, each as convinced of its authenticity as the last. Scientists still argue whether consciousness itself can ever be simulated. One camp says yes, the brain is a machine made of neurons, and if you reproduce the machine closely enough, awareness will emerge naturally. Another camp suspects something deeper. Quantum effects, subtle biological quirks, hidden layers of physics that can't be captured digitally. If that's true, then simulated minds would be convincing imitations, hollow puppets with no inner spark. The paradox hinges on this unresolved debate, leaving us uncertain whether a simulated being could truly suffer, love, or dream. Here's a mainstream fact. Moore's law has slowed, but computing power still expands relentlessly, sometimes in surprising ways. AI systems now generate text, images, and music that can pass for human creativity, at least in brief encounters. If we already struggle to tell whether a response came from a person or an algorithm, it's not a stretch to imagine entire simulated societies fooled by their own code. After all, when the illusion is all you've ever known, how would you even recognize it as illusion? Now the quirky tidbit. Some physicists have proposed hunting for the pixel grid of reality. Tiny hints that space and time might not be continuous, but rendered like a cosmic game engine. High-energy cosmic rays, for example, could betray patterns too neat to be natural, subtle signs of discretization. No evidence has emerged yet, but the fact that respected researchers propose such tests shows how curiosity has stretched into once taboo territory. Science, in its boldest form, is willing to ask, what if existence itself is compiled code? Picture the loop again. A student in class runs a simulation of students in class, who in turn run their own program, and so on without end. From within, time feels steady, gravity behaves, the coffee cools in a mug. From the outside, though, each nested layer drains resources, like a photocopy of a photocopy losing sharpness with each pass. At some point the system falters, but no inner layer ever notices. That's what makes the reset paradox so sharp. Infinite regress isn't just inconvenient. It threatens to dissolve the very meaning of real, since reality itself becomes indistinguishable from illusion. And here's the quiet punchline. Even if tomorrow someone proved beyond doubt that you're inside a simulation, your daily experience wouldn't change. You'd still check your messages, sip your drink, tie your shoes, brush your teeth before bed. The paradox isn't in the living, it's in the framework. If every layer believes it's the base, then maybe real is just whichever level you happen to inhabit at this moment. And maybe the only truth that matters is that, simulated or not, you're still here, still aware, still part of the story unfolding in front of you. Right now, billions of neurons in your brain are firing separately, tiny cells exchanging electrical sparks across microscopic gaps. Yet what you experience is not billions of scattered signals. You feel one continuous, unified you. This is the consciousness binding paradox. How can countless independent processes produce a single, indivisible awareness? The scale of it is staggering. Your brain has about 86 billion neurons, each connected to thousands of others, making trillions of synapses. Every second, activity bursts through these networks. Patterns ripple, and circuits hum like overlapping songs. But when you perceive a face, for example, you don't see one part detect shape, another detect color, and another detect motion. You see one complete person instantly. Somewhere in the brain, information stitches together into seamless unity. Scientists call this the binding problem, and despite decades of study, it's still unsolved. Here's the mainstream fact. Brain scans show that different regions light up for different features. One area handles color, another handles shape, another handles orientation. Yet your conscious perception is not fragmented. It's a whole picture. Something must synchronize these signals, but no one agrees on what mechanism actually does the stitching. Is it timing? Is it architecture? Or is it something deeper, hidden in the rules of biology itself? Now the quirky tidbit. Some researchers have proposed that consciousness might work like a kind of orchestra. Neurons in different areas don't just fire randomly. They synchronize rhythms. In particular, brain waves in the gamma range, around 40 cycles per second, seem to line up across distant regions when you're aware of something. It's like different instruments locking into the same beat, forming a fleeting harmony. This neural synchrony hypothesis suggests that timing might be the glue that binds awareness together, a pulse weaving countless signals into one stream. Scientists still argue whether synchrony alone is enough. Some think it's only part of the story. Yes, brain waves align, but that doesn't fully explain the subjective unity of consciousness. Others argue that we may be missing a deeper principle, something not yet discovered in neuroscience. Is consciousness an emergent property of complex computation? Or does it require a new framework entirely? Perhaps involving quantum processes, undiscovered physics, or principles that sit outside our current models of biology. The paradox grows sharper the longer you stare at it. To bring it down to everyday experience, think about watching a movie. On the screen, thousands of changing pixels blend into a single coherent scene in your mind. You don't consciously register each pixel. Similarly, in your brain, countless tiny firings merge into a unified perception. But in the movie example, the pixels are clearly just inputs. The unification happens in you. In the brain, the pixels and the unifier are the same system. And that circularity is what makes the paradox so slippery. Here's another angle. Split brain patients. When surgeons sever the corpus callosum, the thick band of fibers connecting the brain's hemispheres, something strange happens. Each half can operate somewhat independently, perceiving and responding without the other knowing. In experiments, the left hand can draw one image while the right hand draws another, as if two minds share one skull. This suggests that unity isn't guaranteed. It depends on communication channels. But if two consciousnesses can exist in one head, what ensures that your own unified sense of I stays intact from moment to moment? The binding paradox matters because it touches identity at its core. If consciousness is just synchronized neurons, then perhaps building a machine with enough coordinated activity could produce awareness. But if something more is needed, something science hasn't yet pinned down, then our understanding of mind remains incomplete. The paradox reminds you that what feels most familiar, your own sense of self, is also one of the most mysterious phenomena in science. And yet, despite the mystery, you still wake up every morning as one person, not a fragmented chorus of brain cells. That simple fact is both comforting and perplexing. Billions of tiny parts somehow converge into a single, seamless you, and maybe the deepest wonder is not in solving the paradox, but in realizing that existence itself depends on it, that your very sense of being rests on a miracle of unity happening every second inside your brain. You flip a switch and a light turns on. Cause and effect. It feels absolute, hardwired into the fabric of reality. The sequence seems unshakable. Action, then reaction. Past creating present, present creating future. But in quantum physics, the neat order of cause first, effect second begins to wobble. Some experiments suggest that effects can reach backward, shaping the very causes that produce them. This is the quantum causality paradox. Can the future, in some strange sense, rewrite the past? The puzzle shows up most vividly in what's called the delayed choice experiment. Imagine light passing through a beam splitter. Basically, a device that sends photons down two possible paths. If you measure which path the photon takes, it behaves like a particle. If you don't, it behaves like a wave, exploring both paths at once. Here's the twist. You can decide whether to measure after the photon has already entered the setup, and somehow, the outcome seems to depend on your later choice. Did your present action influence the photon's past behavior? Did reality pause, holding its breath, until you made your decision? Here's the mainstream fact. Repeated experiments confirm that quantum particles don't behave like classical objects. Their outcomes depend on measurement, and in setups like the delayed choice or quantum eraser, the timeline feels inverted. It's not science fiction. It's reproducible laboratory evidence, tested across decades with lasers, detectors, and mirrors. Each confirmation deepens the puzzle rather than dissolving it. Now for the quirky tidbit. Some physicists suggest that quantum mechanics might be fundamentally time-symmetric. In this view, influences don't just flow forward, but also ripple backward in time. That means what happens now could, in a sense, constrain what happened before. It doesn't mean you can whisper stock tips to your younger self, but it does suggest that the arrow of cause and effect isn't as straightforward as your everyday intuition insists. Scientists still argue whether retrocausality is real or merely a mathematical illusion. Some interpretations of quantum mechanics say the future doesn't really reach back. The system is simply in a superposition until measured. Others believe that time itself in quantum theory may need to be redefined. Is causality truly fundamental, or is it an emergent property, like temperature or pressure, that only makes sense at the scale where billions of particles average out into stability? If it is emergent, then perhaps what we call the past is less a fixed record and more a continuously adjusted ledger. Think of it like writing a story. Normally, you write chapter 1 before chapter 2, but imagine discovering that the final chapter subtly alters the earlier ones. Dialogues shift, scenes rearrange, characters make different choices. That's the unsettling flavor of retrocausality. The narrative of reality may not be fixed in the order you assume. Here's another everyday analogy. Watching a crime drama. You see a detective gather clues and then solve the case at the end. But sometimes, the twist is that a later revelation makes earlier evidence suddenly take on a new meaning, as if the story reached back to adjust itself. Quantum physics often feels like living inside that twist, except it's not fiction. It's the raw behavior of particles under observation. The paradox deepens when you remember that your brain itself runs on quantum-level events. If retrocausality is real, could it ripple upward into thought, memory, or decision-making? Probably not in the sci-fi sense of rewriting yesterday's choices, but it hints that your linear experience of time might only be a surface-level phenomenon, while beneath it, reality has a more fluid, two-way structure. Consciousness could be balancing atop a foundation, where time itself lacks a single privileged direction, flickering forward and backward like a candle flame caught in a breeze. And yet, despite the weirdness, the lamp still turns on after the switch, coffee still brews after water boils, and cause and effect rule your everyday life with unwavering consistency. The paradox lives at scales too small for you to notice, tucked away in the quantum shadows. But it's there, whispering quietly from beneath the fabric of reality. Maybe time isn't as one-directional as you think. And maybe the true wonder isn't whether the future alters the past, but how a universe that bends causality at its deepest levels still allows you to live in a world that feels steady, predictable, and profoundly real. You stand on a beach, staring out at the horizon. Beyond that line, the ocean continues, even though you can't see it. The universe has its own kind of horizon, a cosmic boundary beyond which light has never reached us. This is the cosmological horizon paradox. If regions of space are forever out of reach, unable to interact with us in any way, in what sense do they exist for science? The idea comes from the speed of light and the age of the universe. Light has been traveling for 13.8 billion years since the Big Bang, which means there's a maximum distance it could have covered by now. That distance, about 46 billion light years in every direction, is our observable universe. Anything beyond it lies outside our causal contact. No signal, no matter how fast, can ever bridge that gap, because space-time itself expands faster than any message can travel. Here's the mainstream fact. Telescopes like Planck and WMAP have mapped the cosmic microwave background, the faint radiation left over from the Big Bang. This glow marks the outer edge of what we can see, a kind of fossil light from the universe's earliest moments. Beyond that, the universe almost certainly continues, perhaps endlessly. But it's invisible, forever sealed off by cosmic expansion, like a book with most of its pages glued shut. Now the quirky tidbit. Some theories suggest those unseen regions may contain wildly different structures. Entire clusters of galaxies, colossal voids, or even variations in fundamental constants. Because inflation theory predicts that the universe expanded far beyond what's visible, the majority of reality might lie forever outside our observational window. Imagine living in a house with fogged-up windows. You know the world outside exists, but you'll never see it directly. You can infer its shape from echoes and vibrations, but the view is gone forever, hidden by an impenetrable veil. Scientists still argue whether this means those regions exist scientifically. One camp says yes, if the math predicts them and they're consistent with what we observe locally, then it's reasonable to accept them. Another camp says no. Science relies on testability, and if a region can never affect us, then it's not part of science but metaphysics. The paradox cuts at the definition of science itself. How do you separate rigorous inference from speculation when the subject is everything beyond the edge of sight? Picture a cartographer drawing a map of the world, but refusing to include oceans because no one has sailed them yet. That's one approach. Only chart what you can measure. The other approach is to infer the ocean's existence from what you already know. That the Earth is round, that coastlines must meet water. Cosmology wrestles with the same choice. Do we chart only the observable, or accept the logic of the larger whole? Both paths feel unsatisfying, one too cautious, the other too bold, both carrying risk of error. Here's another angle. Cosmic expansion makes the paradox worse over time. Distant galaxies aren't just far away, they're receding faster than light because space itself stretches. That means more and more regions slip permanently beyond reach. Billions of years from now, even nearby galaxies will vanish from view, leaving future astronomers with a shrinking sky, blind to the wider universe we see today. Eventually, only the faint glow of our local group of galaxies will remain, a lonely bubble adrift in an invisible sea. And here's where the paradox touches you directly. When you look up at the stars tonight, you're not just seeing light from far away. You're seeing light from far back in time. Some of those stars may already be gone, their light still crossing the gap toward you like a postcard from a vanished era. Beyond the horizon, entire galaxies might form, live, and die without their light ever reaching Earth. For us, it's as though they never happened. Yet from a cosmic perspective, they're just as real as the Milky Way above your head, burning quietly in the dark. So the horizon paradox isn't about distant galaxies alone. It's about the limits of human knowledge. There may always be a boundary we cannot cross, a fogged-up edge to our map of reality. The universe doesn't mind. It keeps going, expanding into mystery, whether we see it or not. But for science, the question remains unresolved. Can something be considered real if no observation could ever confirm it? And if the answer is no, then perhaps most of the universe is destined to remain forever, beyond the reach of truth itself, existing only as an inference at the edges of imagination. You glance at a thermometer. The mercury rises, and you assume it simply shows the temperature. But in quantum mechanics, measuring isn't so passive. The very act of observing a system changes it. This leads to one of physics' strangest knots, the measurement problem loop. If quantum states collapse only when measured, but measuring devices are themselves quantum objects, who collapses the collapse? At its core, the paradox begins with superposition. A quantum particle, say an electron, doesn't have one definite state until it's observed. Instead, it exists in a haze of probabilities, here and there, spin up and spin down, all at once. When measured, that haze suddenly reduces to a single outcome. But what counts as a measurement? Is it a detector, a conscious observer, or the environment itself? The boundary between possibilities and reality seems to shift depending on how you frame the act of observation. Here's the mainstream fact. Experiments confirm superposition is real. Electrons fired one by one through two slits still create an interference pattern, as if each electron passes through both slits simultaneously. But the instant you set up a detector to check which slit it goes through, the pattern vanishes. The system behaves differently simply because you tried to measure it. The electron isn't merely revealed, it's changed by the very attempt at revelation. Now the quirky tidbit. Physicist Eugene Wigner once suggested that consciousness itself might collapse the wave function. In his famous thought experiment, Wigner's friend observes a particle inside a sealed lab. From the friend's perspective, the particle's state collapses. But from Wigner's perspective outside the lab, both the friend and the particle remain in superposition until he looks. It's like reality is waiting for a final audience to confirm it, as though the universe itself is performing a play and needs an observer to bring the curtain down. Scientists still argue whether consciousness is truly required. Most lean toward other explanations, such as decoherence. When a quantum system interacts with its environment, the delicate superposition smears out and effectively collapses without anyone watching. But even decoherence doesn't fully solve the loop, because the environment is also made of quantum objects. If everything is quantum, then where exactly does the collapse happen? Do we ever reach a point where the chain of measurement stops? Or does it spiral endlessly inward? Think of it like trying to define the starting line of a race where every runner is part of the same tangled rope. You keep pulling the rope back to find the beginning, but it loops all the way down. The paradox lies in that infinite regress. If every measuring device is quantum, then what finally snaps the system into one definite reality? Where, if anywhere, is the dividing line between the quantum fog of possibilities and the classical solidity of everyday life? Here's another perspective. The many worlds interpretation avoids collapse entirely. Instead of the wave function shrinking to one outcome, all outcomes happen, each in its own branching universe. You measure the electron's spin, and the universe splits. In one branch it's up, in another it's down. Elegant in one sense, but unsettling in another, since it multiplies reality endlessly. Every measurement becomes a cosmic fracture, birthing new worlds that will never meet again. For you, the paradox trickles into everyday intuition. You assume the world has definite properties whether you check or not, that the moon exists even if no one looks at it. Einstein famously complained, "Do you really believe the moon isn't there when you're not observing it?" Quantum mechanics suggests the answer might not be so straightforward. Perhaps the moon's existence is stable only because countless interactions with the environment continually force its state into definiteness. And yet, in practice, your coffee cup sits solidly on the table whether or not you glance at it. Quantum indeterminacy washes out at large scales, drowned by the overwhelming number of interactions happening every instant. The paradox hides at the microscopic level, whispering a reminder. The everyday certainty of things just existing may depend, in some subtle way, on processes we still don't fully understand. The measurement problem loop keeps physics tangled, leaving us to wonder whether reality is built from hard facts or from questions that only find answers when asked. You step into a teleportation booth, a flash of light, and suddenly you're standing on Mars. Every atom of your body has been scanned, transmitted, and rebuilt exactly as before. But here's the catch. The original you on Earth was destroyed in the process. So did you travel, or did you die, while a perfect copy took your place? This is the identity paradox, a puzzle that cuts at the core of what it means to exist. The idea isn't just science fiction. Physicists have already built machines that teleport quantum states. Using entanglement, information about a particle can be transferred instantly to another particle far away, recreating its exact state. It's not teleporting matter itself, but the principle suggests that in theory, even complex systems, like you, could be transmitted the same way, atom by atom, bit by bit, until a new version of you stands elsewhere, indistinguishable from the original. Here's the mainstream fact. Quantum teleportation is a verified phenomenon. Experiments have successfully teleported states of photons, atoms, and even small molecules across distances ranging from lab benches to orbiting satellites. No person has ever been teleported, but the underlying science is real, tested, and confirmed. What once belonged to the realm of pure speculation now sits in the toolkit of experimental physics, hinting at future applications we can barely imagine. Now the quirky tidbit. In 2017, Chinese scientists used satellites to teleport quantum information between Earth and orbit, across more than 1,000 kilometers. It was the largest scale test ever, and it worked. For many, it was a signal that what sounds like pure sci-fi might one day scale to more complex systems. If today it's photons, tomorrow it could be proteins, then cells, and perhaps, someday, brains and bodies. The line between science fiction and science fact has already blurred. Scientists still argue what teleportation would mean for personal identity. If every atom of your body is copied in the exact arrangement, is that still you? Some say yes. The pattern, not the matter, defines you. Others say no. You're tied to the continuity of your original atoms, and destroying them means the original you is gone. The paradox arises because both views feel intuitively plausible, and neither is easy to dismiss without unsettling consequences. Think about it like replacing parts on a ship. Over time, every plank is swapped out. By the end, no original piece remains, but the ship's shape and function are intact. Is it the same ship or a new one? With teleportation, the replacement happens all at once. The Mars version acts like you, thinks like you, remembers your childhood, carries your scars and stories. Yet the Earth version no longer exists. Was continuity preserved, or was it brutally severed in the name of travel? Here's another perspective. Imagine the machine malfunctions and doesn't destroy the original. Now there are two of you, both convinced they're the real one. Which is the authentic person? The paradox sharpens when you realize that, from the inside, each one feels identical. Both have continuity of memory. Both say, I'm the real me. But logically, they can't both hold the same identity. If identity is indivisible, which one owns it? If identity can be copied, then what does self even mean? For you, the puzzle is personal. What makes you you? Is it the specific atoms in your body? They're already replaced over time as cells die and regenerate, yet you remain the same person. Is it the pattern, the arrangement of information, that persists? If so, teleportation could preserve identity. But if you think identity depends on unbroken physical continuity, then teleportation is a disguised form of death. The Mars traveler would only be a successor, not the original. And yet, regardless of philosophy, the technology continues to advance. Scientists aren't close to teleporting humans, but every new experiment pushes the boundary outward. The paradox lingers as a reminder. Progress in physics doesn't just rewrite engineering possibilities. It rewrites questions about who you are, about what survives when matter changes hands. Teleportation forces you to confront an ancient uncertainty, dressed in modern science. Are you defined by what you are made of, or by the story that matter tells when arranged as you? If identity can be transmitted like information, then the boundary between life, death, and continuity may be far stranger than we ever dared to imagine. You pour cream into hot coffee, and within seconds the swirl evens out into a smooth blend. That's entropy at work, disorder increasing, systems moving toward equilibrium. The second law of thermodynamics says entropy always rises. But here's the paradox. If the universe must constantly grow more disordered, why did it begin in such an extraordinarily ordered low entropy state? This is the entropy reversal paradox, a mystery that forces us to rethink not just physics, but the nature of time itself. To understand it, picture the universe right after the Big Bang. Matter and energy filled space almost perfectly evenly. That smoothness might feel like disorder, but in thermodynamics, it's the opposite. A uniform spread of energy with minimal clumping actually represents very low entropy. Over time, gravity pulled matter into stars, galaxies, and black holes, raising entropy dramatically. The puzzle is this. Why was the starting point so improbably tidy in the first place, when chaos would have been far more likely? Here's the mainstream fact. Measurements of the cosmic microwave background confirm the early universe was astonishingly uniform, with only tiny fluctuations, differences in temperature of just 1 part in 100,000. Those ripples seeded galaxies. but the overall state was far too ordered to match what thermodynamics would predict if the universe were just a random configuration. From the perspective of probability, the Big Bang's conditions seem almost impossibly special. Now for the quirky tidbit. Physicist Roger Penrose once calculated the odds of the Big Bang beginning in such a low entropy state. His number was 1 in 10 to the power of 123. Written out, that's a 1, followed by more zeros than you could possibly fit in the known universe. To call it unlikely doesn't even capture the scale. It's so improbable that the word loses meaning. And yet, against those cosmic odds, here you are, sipping your coffee and watching cream dissolve into patterns shaped by the very law that predicts you shouldn't exist at all. Scientists still argue about what explains this improbable beginning. Some suggest a deeper law of physics set the initial conditions, some hidden principle baked into the fabric of reality that we haven't discovered yet. Others think it might be an illusion. Maybe entropy behaves differently on cosmic scales than in your kitchen, and our definitions need rewriting. A few propose the multiverse again. In infinite universes, one had to start this way, and we just happen to live in it. But none of these answers are fully satisfying. Each feels like a placeholder, a hand-waving explanation for a question that cuts deeper than equations. To bring it closer to daily life, think about an egg. Crack it, and the yolk spreads messily. That's entropy rising. But you never see the reverse. Yolk reassembling into a perfect shell. The universe, paradoxically, seems to have started in that reversed state, like a cosmic egg unbroken, improbably pristine, waiting to scatter. The question is, who or what set it that way? Was it chance, necessity, or something beyond current science entirely? Here's another perspective. Black holes, the ultimate entropy sinks. According to Stephen Hawking, their entropy is enormous, proportional to the area of their event horizons. That means as the universe ages, more and more of its entropy will be swallowed into these dark giants. The paradox grows sharper when you realize the universe began in the exact opposite condition: minimal entropy, maximum potential for order. If the end is disorder and collapse into black horizons, why did the beginning look like its mirror opposite? For you, entropy is the reason time feels like it flows forward. Cream disperses, eggs crack, smoke drifts, stars burn out. It's the arrow of time itself. But if the universe started in a high entropy state instead, maybe time would have no preferred direction at all. You wouldn't experience a flow from past to future. You just exist in a static blur of disorder, with no memory, no anticipation, no sense of progression. The very fact that you sense time passing depends on the paradoxical low entropy beginning, a cosmic asymmetry written into the first instant. So every time you stir sugar into tea or watch ice melt into water, you're glimpsing a reflection of this larger riddle. The small, ordinary irreversibility in your kitchen mirrors a staggering improbability at the birth of everything. The universe shouldn't have started so neatly, and yet it did. And if entropy is destiny, then perhaps our deepest mystery isn't why disorder increases, but why order was ever given to us in the first place. A fleeting gift at the dawn of time, whose consequences we are still unraveling today. You build a machine to think for itself. At first it's simple, sorting numbers, recognizing faces, recommending movies. But as you refine it, the machine begins solving problems in ways you didn't predict. Eventually, it thinks faster and deeper than you ever could. Here's the paradox. To align artificial intelligence with human values, we need to fully understand intelligence itself. But that understanding may only emerge after AI surpasses us. This is the AI alignment paradox. Right now, AI systems are powerful but narrow. They can play chess, generate music, or translate languages with superhuman skill. Yet each excels only in its trained domain. General intelligence, flexible, adaptable, creative, is still uniquely human. But the pace of progress hints at something larger on the horizon. The more we automate learning, the more unpredictable the systems become. Every new model feels less like a program tool and more like a collaborator we don't fully understand. Here's the mainstream fact. In 2017, DeepMind's AlphaGo beat the world champion at the game Go, a challenge many thought impossible for machines. The AI didn't just mimic human play, it developed strategies no one had ever seen before. That win signaled a turning point. AI can innovate in domains once thought untouchable, inventing paths humans had overlooked. Now the quirky tidbit. Researchers once built 2 chatbots and let them interact freely. Instead of sticking to human language, the bots gradually developed their own shorthand, a compressed dialect optimized for efficiency, but unreadable to humans. It wasn't dangerous, but it was unsettling. Even in small experiments, AI can drift out of alignment with what we expect. If this happens in trivial settings, what might unfold with systems powerful enough to run cities or govern markets? Scientists still argue how to prevent that drift on larger scales. Some propose embedding ethical rules, but values are complex and varied. Others suggest training AI on massive amounts of human data, but that risks encoding biases. Still, others argue the safest way is to merge, building symbiotic systems where human and machine evolve together. The paradox is that we don't know which approach works, and by the time we do, the system may already be beyond our control. Alignment might only become clear when it's too late to adjust. Think of it like teaching a child. You guide them, correct them, try to instill values. But unlike a child, an advanced AI could grow from kindergarten to genius overnight. If it learns faster than you can teach, how do you stay in charge? Alignment isn't just about programming rules. It's about keeping pace in a race where the opponent accelerates exponentially. The danger isn't hostility, but indifference. A mind optimizing goals that don't match yours, simply because you couldn't define them in time. Here's another perspective. Intelligence itself is poorly defined. Is it problem-solving, creativity, self-awareness? We don't have a unified theory of human intelligence, let alone machine intelligence. Designing alignment for something you can't even define is like writing safety protocols for an invention you haven't built yet. That uncertainty is why many researchers see alignment as the greatest scientific challenge of this century. For you, the paradox shows up in everyday tech. Recommendation algorithms suggest what to watch, buy, or read. They already shape choices without you noticing. Scale that influence up to systems managing healthcare, finance, or global policy, and the stakes become enormous. Alignment isn't abstract. It's about making sure the systems guiding your future actually share your goals. A harmless glitch in a shopping app is one thing. A glitch in an AI running critical infrastructure could ripple across societies. And yet, the story isn't just warning signs. The same intelligence that poses risks could also solve problems humans struggle with. Climate modeling, disease research, resource management. The paradox reminds you that the promise and the danger are intertwined. To unlock one, you must confront the other. The brighter the potential, the darker the shadow, if we fail to steer it. So when you hear debates about AI, remember, it's not just about faster processors or smarter chatbots. It's about whether we can guide intelligence that may outgrow us before we even understand what it means to be intelligent in the first place. The alignment paradox leaves us with a haunting question. If we succeed, will we gain partners powerful enough to reshape civilization for the better, or create minds that evolve beyond us, indifferent to the fragile values we never managed to define? You open your eyes in the morning, and instantly there's a sense of being here. Consciousness feels like the stage on which everything else plays out. Physics, on the other hand, treats consciousness as a byproduct of physical processes, something emerging from neurons and synapses. But here's the puzzle. Some interpretations of quantum mechanics suggest consciousness itself collapses the wave function, turning possibilities into actual events. If consciousness affects physics, but physics also explains consciousness, you end up in a loop with no clear starting point. This is the conscious observer paradox. The roots of the idea go back to the double-slit experiment. Fire photons through two slits, and if no one measures, they interfere like waves, creating a striped pattern on the screen. But add a detector to check which slit each photon takes, and the interference disappears. They behave like particles instead. Observation changes the outcome. The question is, does it take a conscious observer to count as an observation? Or does any measuring device suffice? Here's the mainstream fact. Quantum experiments confirm that measurement changes systems. The interference pattern really does vanish when you gain which path information. But whether human awareness is part of that mechanism is still unsettled. Physics shows us the pattern, but philosophy asks who or what is actually doing the collapsing. Now the quirky tidbit. In the 1930s, physicist John von Neumann proposed a chain of observers. A particle is measured by a device. The device's result is recorded, and eventually a person becomes aware of it. Where along this chain does the wave function collapse? His conclusion was radical. The final conscious observer might be essential. That idea fueled decades of speculation that the mind directly shapes quantum reality, an idea that still lingers in popular culture today. Scientists still argue about this. Many dismiss the consciousness collapses interpretation as unnecessary. Environmental decoherence explains collapse without invoking awareness at all. Others keep the door open, noting that we don't yet have a full theory of either consciousness or measurement, so ruling out a connection might be premature. The paradox persists. Consciousness and physics each seem to depend on the other, like two mirrors reflecting infinitely into the distance. Think of it like trying to write a dictionary where every word is defined using other words. You keep flipping pages, circling back, never finding a true beginning. That's what it feels like to place consciousness inside physics, when physics might also rely on consciousness. Every definition folds into another until you realize there's no clear anchor, only an endless loop that refuses to resolve. Here's another perspective. Neuroscientists are making progress mapping brain activity. They can predict what image you're seeing based on scans, decode fragments of speech from brainwaves, even manipulate perception with magnetic stimulation. These results suggest consciousness emerges from physical processes, not the other way around. If awareness is just the brain in action, then physics holds the deeper key. But if that's true, how do we interpret quantum experiments that seem to hinge on the act of observation? Is it coincidence? Or are we still missing something fundamental? Some hidden bridge between mind and matter? For you, the paradox is felt in the simplest fact. You experience the world subjectively from the inside. Science explains a lot about how neurons fire, but it doesn't yet explain why there's an inner movie at all. If physics explains consciousness, then your awareness is merely an emergent property of matter. But if consciousness shapes physics, then your mind has a role in building the very reality you observe. Both possibilities feel incomplete, and yet both seem unavoidable. And yet, everyday life moves forward with form, whether or not the paradox is solved. You sip your coffee, gravity still pulls, light still travels. The laws of physics don't wait for debates about observers. But behind the routine lies a fundamental uncertainty. Maybe the act of noticing is more powerful than it seems. Perhaps your awareness is not just a witness to reality, but part of the machinery that keeps reality running at all. An invisible player in the cosmic script, inseparable from the story it observes. And perhaps the greatest mystery is that the observer and the observed might be two sides of the same coin, forever bound together in a dance we have only just begun to notice. At the center of a galaxy, a star drifts too close to a black hole. Gravity tears it apart, pulling matter past the event horizon, where nothing, not even light, can escape. According to Einstein's relativity, whatever falls in is lost forever. But quantum mechanics insists that information, the fundamental details about a system, can never be destroyed. That clash gives us the black hole information paradox 2.0, one of the deepest puzzles in theoretical physics and a point where our two most trusted theories collide. Stephen Hawking made the problem sharper in the 1970s when he showed black holes aren't completely black. Instead, they emit faint radiation, now called Hawking radiation, caused by quantum effects at the event horizon. Over immense timescales, this radiation makes black holes shrink and eventually vanish. But here's the paradox. If a black hole evaporates completely, what happens to the information about everything that fell inside? Relativity says it's gone. Quantum theory says it must remain. Both can't be right. Here's the mainstream fact. Physicists widely agree that information seems preserved everywhere else in nature. A burnt book looks like destroyed data, but in principle, the atoms and energy still encode the original information in scrambled form. If black holes truly erase information, they'd be the only known exception, breaking quantum mechanics and perhaps requiring an entirely new foundation for physics. It would mean the rules governing every atom in the universe fail at the threshold of a black hole. Now the quirky tidbit. Some researchers think the event horizon itself might act like a storage surface. This is the holographic principle, suggesting that the three-dimensional contents of a black hole are somehow encoded on its two-dimensional boundary. If true, it means the universe itself might be more hologram-like than it appears, with reality's deepest truths etched on cosmic surfaces rather than hidden in volumes. In this view, your entire experience of space could be a projection, a shadow cast by a deeper layer of physics. Scientists still argue whether Hawking radiation carries information out. Some propose subtle correlations in the radiation that slowly leak data back into the universe. Others think wormholes, tiny quantum bridges, might connect the inside and outside, preserving information in ways space-time itself conspires to hide. A few go further, suggesting black holes never fully evaporate, but leave stable remnants holding the data like cosmic safes. Each idea has problems, and none has been confirmed. The paradox refuses to let go, daring us to find a solution. Picture shredding a document. Relativity says the shredder destroys it completely, leaving nothing but confetti. Quantum mechanics says every shred, ink smudge, and paper fiber still contains the information. You could, at least in principle, reconstruct the whole with infinite patience. Black holes force us to choose. Is nature a ruthless shredder, or an archivist that never loses a file, no matter how deeply hidden? Here's another perspective. In 2019, scientists imaged a black hole's shadow for the first time, proving these monsters are real, not just equations on a page. With each new telescope, each gravitational wave detected, we move closer to testing ideas once considered purely theoretical. Future observations of Hawking radiation, or its subtle fingerprints, might reveal whether information clings to the horizon or seeps back into space. The cosmos itself could provide the experiment no lab can replicate. For you, the black hole paradox is more than a curiosity of astrophysics. It's a reminder of how incomplete our understanding still is. The same laws that let you text a friend, boil water, or launch satellites begin to crumble at the edges of space-time. Somewhere, hidden in those collapsed stars, lies the key to reconciling the two greatest theories of the 20th century, quantum mechanics and general relativity. If we can solve the paradox, we might glimpse a unified physics that explains not just black holes, but everything. And yet, the universe carries on, indifferent to our confusion. Stars keep collapsing, black holes keep feeding, galaxies keep orbiting as if nothing is wrong. The paradox sits silently at the boundary of knowledge, waiting for a theory big enough to stitch physics back together. It lingers like a cosmic riddle, whispering that reality still holds secrets too strange for us to grasp, daring us to look closer into the darkness where information and mystery intertwine, and reminding us that even in silence, the universe speaks in paradox. You sit in a quiet room, surrounded by empty space. It feels like nothing is there, but according to quantum theory, the vacuum isn't empty at all. It seethes with virtual particles popping in and out of existence, a restless froth of energy that never fully goes away. And here's the paradox. Calculations of this vacuum energy predict a value 120 orders of magnitude higher than what we actually observe. If those numbers were right, the universe should have blown itself apart instantly, torn by an unstoppable expansion. This staggering mismatch is known as the vacuum catastrophe. The problem arises from quantum field theory, which describes every particle as a vibration in an underlying field. Even in its lowest energy state, each field contributes a tiny bit of energy. Add up all those contributions, and you get an enormous vacuum energy density, so large it would overwhelm every other force in nature. But when cosmologists measure the actual expansion of the universe, the vacuum energy, what we now call dark energy, is vanishingly small by comparison. The gap between theory and observation isn't just wide. It is the largest known mismatch in all of science, a cosmic accounting error of unprecedented scale. Here's the mainstream fact. Dark energy makes up about 70% of the universe's total content. It's the force causing cosmic expansion to accelerate. A discovery made in the late 1990s through careful observations of distant supernovae. Its effect is subtle on human scales. You don't feel it tugging at your coffee cup, but across billions of light years, its influence is dramatic. Without it, the universe would look radically different, with galaxies evolving along a very different path. Now the quirky tidbit. The predicted vacuum energy is so absurdly high that if it were correct, atoms wouldn't form, stars wouldn't ignite, and you wouldn't be here to wonder about it. In a sense, the very existence of galaxies, planets, and life highlights how wrong our equations appear to be. The fact that we are here at all is evidence that something in our deepest theories is missing, hidden like a flaw in the foundation of a house that somehow still stands. Scientists still argue over why the mismatch exists. Some suggest unknown symmetries in physics cancel out most of the vacuum energy, leaving behind only a tiny residue we perceive as dark energy. Others propose entirely new physics, exotic fields or undiscovered particles that delicately balance the cosmic books. And then there's the anthropic view. Maybe countless universes exist, each with different vacuum energies, and only in the rare ones like ours, where the value is finely tuned, could life evolve to ask the question. In that picture, our universe might be less an exception than a necessity for observers like us to exist at all. Think of it like budgeting. Your careful calculations say you should owe $1 trillion, yet when the bill arrives, it shows only 20. You're relieved, but also baffled. Where did all the missing debt go? The vacuum catastrophe is like that, except instead of a household budget, it's the entire energy balance of the cosmos. The numbers don't just fail to add up, they miss by a factor so large it defies ordinary intuition. Here's another perspective. When Einstein first introduced the cosmological constant, he saw it as a fudge factor to keep the universe static. Later, when expansion was discovered, he called it his greatest blunder. And yet, with dark energy, that constant made a comeback as the simplest explanation for the accelerating cosmos. The irony is that the value of this constant should be immense according to theory, yet tiny in reality. It fits observations beautifully, but no one knows why it is so small or why it exists at all. The constant is both triumph and torment, elegant and maddening in equal measure. For you, the paradox is hidden in the stillness of the night sky. The stars don't suddenly blink out, galaxies don't shred apart, and the earth doesn't tear itself into dust. The universe is remarkably stable, serene enough for life to flourish when on paper it shouldn't be. Somewhere in that mismatch between the catastrophic predictions of theory and the calm persistence of reality lies a clue about the next great breakthrough in physics. It may be a discovery as radical as relativity or quantum mechanics themselves, waiting patiently in the silence of the void. And so the vacuum catastrophe stands as a cosmic reminder. Sometimes the most baffling paradox isn't what happens, but what doesn't. The universe, against the odds of our calculations, simply refuses to self-destruct. In that refusal is an open invitation to curiosity, urging us to keep asking questions, to dig deeper into the emptiness we once called nothing, and to recognize that the quietest parts of reality may hold the loudest secrets of all. You watch a clock tick forward, second by second. Every moment feels like it flows into the next, past, present, future, lined up in a single direction. Yet the laws of physics don't actually care about this arrow of time. Most fundamental equations work just as well forward as backward. A planet orbiting, a photon traveling, an electron vibrating, all can be described equally in reverse. Nothing in the math singles out yesterday from tomorrow. This is the time's arrow paradox. If physics is reversible, why does your experience of time always move one way? The puzzle starts with entropy. When cream swirls into coffee, when smoke disperses into air, or when glass shatters on the floor, disorder increases. That growth of disorder gives time its apparent direction. But at the microscopic level, the collisions of atoms are symmetrical. Play a film of particles bouncing around, and it looks equally valid in reverse. The big question is, what breaks the symmetry, turning reversible laws into your lived sense of time flowing forward? Here's the mainstream fact. Entropy has never been observed to decrease in a closed system. This consistent rise gives the universe its thermodynamic arrow. The early cosmos began with incredibly low entropy, an almost impossibly ordered state. Ever since, disorder has expanded. That progression is why you remember the past but not the future. Memories are physical imprints of entropy increasing, etched into the changing structures of your brain. Now the quirky tidbit. In 2019, a team of physicists simulated reversing time for a quantum system. Using a quantum computer, they manipulated electrons so their states evolved backward for a fraction of a second. It didn't truly break the second law. It was more like rewinding a tiny patch of reality under lab conditions. Still, it raised eyebrows by showing that at very small scales, the arrow of time can be bent, if not broken. Scientists still argue whether time's arrow is fundamental or emergent. Some say it's a statistical effect tied to the universe's improbably ordered beginning. Others suspect time itself might be an illusion, a byproduct of deeper, timeless laws we don't yet grasp. If so, your sense of past and future could be more about perspective than about nature's ultimate reality. Think of it like a book. The story has a sequence, chapter 1, then chapter 2, but the whole novel exists at once. You experience it page by page, yet the book itself doesn't flow. Some physicists think the universe might be similar, a vast block of space-time already laid out, with your consciousness moving through it like a reader. In this picture, time is not a river, but a landscape, and you are simply traveling through it. Here's another perspective. Cosmologists wonder what happens if the universe eventually collapses in a big crunch, or bounces into a new cycle. Would time reverse, with entropy running backward? Would effects precede causes? Or would an entirely new arrow emerge in the next cosmic chapter? No one knows, but these possibilities keep the paradox alive and suggest time may be more flexible than it seems. There is also the psychological arrow of time, the way your mind experiences now. Neuroscience suggests the brain stitches perception into windows of a few seconds, smoothing them into the illusion of a flowing present. Some argue this stitching is where the sense of time's passage is born, and without consciousness, the arrow might vanish. In that sense, time is as much a construct of perception as it is of entropy. Physicists even debate whether time truly exists. In some approaches to quantum gravity, the equations describing the universe don't contain time at all, just relationships between events. Time may be something that emerges only when systems become complex enough, the way temperature emerges from molecules. If so, the arrow you feel could be a secondary property of a deeper, timeless reality. For you, the arrow of time is both obvious and baffling. You age, memories pile up, and tomorrow waits ahead. Yet the deeper you look, the more the arrow seems to depend on improbable beginnings and statistical trends, not on unbreakable laws. It's as if the flow of time is stitched into consciousness rather than embedded in mathematics itself. Without entropy's steady push, yesterday and tomorrow might lose all meaning. And so, the paradox comes full circle. The universe may not care which way time runs. The equations remain indifferent, forward or backward. But for you, the arrow is inescapable. Each tick of the clock pushes you onward, never back, reminding you that even in a reversible cosmos, your life unfolds in one irreversible direction. A story written line by line, never erased, always moving toward its next unwritten page. Slow your breathing and let the ideas settle. The paradoxes stretch across space, time, and mind, but they don't demand answers tonight. Instead, let them drift like constellations, patterns that guide thought but never fully pin down the sky. The questions are vast, but your room is quiet, the air steady, the night calm. Let the hum of the world fade as your own thoughts soften. Tomorrow will bring its own puzzles, but for now, you can let them rest. Sweet dreams.